Good morning, everyone. Thank you for joining today's webinar on Prognostics and Health Management, commonly known as PHM, and its role in transforming industrial maintenance practices. Today, I, Arsh Nadkarni, and Gabby Galvin will be talking about how PHM, supported by IEEE 1856 PHM standard, is revolutionizing maintenance strategies to reduce failures, minimize costs, and optimize asset performance. With industries increasingly relying on automated systems and critical assets like engines, turbines, and heavy machinery, unplanned failures can oftentimes result in substantial financial and operational losses. PHM bridges this gap by enabling organizations to predict failures, plan maintenance, and increase operational reliability. Today in this webinar, we'll cover what PHM is, talk about the evolution of maintenance practices, talk about CBM, which is condition-based maintenance versus PHM, some challenges in implementing PHM for system. Then we'll go into an overview of the IEEE 1856 2017 PHM standard, look at the importance of PHM for rotating and other components, look at a couple key technologies enabling PHM system, finally look at future trends in PHM, and then we'll end with a summary and then any questions. So yeah, let's dive in. Before we dive into the actual webinar content, a little bit about our company here. So Ridgetop Group was founded in 2000 and we're headquartered here in Tucson in Southern Arizona. We're a technology leader in reliability engineering, quality assurance, condition-based maintenance, CBM, prognostic health management, PHM, and integrative vehicle health management, IVHM applications. We offer engineering design services and circuitry for harsh environments, as well as diagnostic and prognostic solutions. We are AS9100D and ISO 9001 QMS certified by MCNA. And shown below here are the market segments that we service worldwide. Shown to the right here is our facility in Tucson here. So what is PHM? Prognostics and Health Management is a systematic approach to monitor and manage the health of critical systems. It combines real-time monitoring, fault diagnostics, and predictive analytics to determine the current health and estimate the remaining useful life, state of health, and other key metrics for certain assets. What makes PHM revolutionary is its ability to transition industries from reactive or time-based maintenance strategies to predictive maintenance. Unlike traditional methods where maintenance occurs after a failure or based on a fixed schedule, PHM uses live data from sensors and machine learning models to predict failures before they happen. For example, in a wind turbine, PHM might analyze vibrations, blade stress, and rotational speeds to identify early signs of wear or misalignment. By predicting failure weeks or even months in advance, operators can schedule repairs during off-peak times, reducing costs and improving the overall energy output of their systems. This approach is essential in sectors such as aerospace, manufacturing, automotive, and energy, where a single failure can cost millions of dollars and compromise safety. Um, the use of PHM systems has proven to reduce maintenance costs by up to 20 to 30% and enhance asset utilization by minimizing unplanned downtimes. Shown here to the right is Ridgetop's PHM framework that is used across different product lines. It consists of six main elements, namely the sensor framework, the control and data flow framework, the feature vector framework, the prediction framework, the fault management framework, and then the performance validation framework. Together, these are key elements that help our systems perform the PHM processes. So now let's look at the evolution of maintenance practices. Maintenance strategies have evolved dramatically over the last century. So we have we have actually four main maintenance practices. The first one is reactive maintenance. So early on, most industries adopted a run to failure approach, fixing equipment only after it failed. While simple, this strategy led to unplanned downtime, expensive repair, and unwanted operational disruptions. Um, Going into the 20th century, uh, uh, we saw the rise of time-based maintenance, where assets were serviced at fixed intervals. This is called preventative maintenance, and although more systematic, this approach often resulted in unnecessary maintenance, wasted resources, and added higher costs. Next is CBM, which is condition-based maintenance. CBM marked a shift toward real-time monitoring of asset condition using sensors and diagnostics. Maintenance was performed based on actual asset conditions rather than going off of time schedules. And today we have a PHM, which is Prognostics and Health Management, and it represents the cutting edge solution for reliability. And not only monitors real time conditions, but also uses advanced analytics to predict failures and estimate key metrics such as remaining useful life, state of health, and prognostic horizon with high accuracy. The benefits of PHM are significant. Studies show that PHM can reduce maintenance costs by up to 20 to 30%, improve equipment uptime by 70%, and increase asset lifespan by about 25 to 50%. This is why industries are rapidly adopting PHM solutions to gain a competitive edge. Now, let's look at the key differences between condition-based maintenance and prognostics and health management. Both of these strategies aim to improve asset reliability, but they do so in distinct ways. CBM is reactive, which means maintenance is triggered when a sensor detects that an asset has reached a specific threshold. An example of this would be abnormal vibration or temperature. It ensures that maintenance happens only when equipment shows signs of potential failure. However, it can miss early stage issues that occur between inspections or rely too much on preset thresholds, potentially leading to unnecessary or missed maintenance. In contrast, PHM is proactive. It predicts future failures by analyzing trends in the asset's data using advanced algorithms and machine learning. With PHM, you get predictions on the RUL and SOH, that is the remaining useful life and state of health of an asset, allowing for precise data-driven maintenance scheduling before failures occur. It optimizes resource allocation and reduces downtime by forecasting when parts will need to be replaced or repaired. To summarize again, CBM is based on monitoring real-time conditions and performing maintenance when thresholds are exceeded, whereas PHM goes a step further by predicting failures in advance, providing better planning for maintenance and reducing unexpected downtimes. PHM offers the advantage of more accurate failure predictions and cost savings through optimized maintenance schedules, while CBM provides simplicity and is more suitable for less complex systems. While CBM is a useful first step, PHM brings enhanced forecasting capabilities, making it more effective for complex and more mission-critical systems. Shown here is the overall process of how this is done. Um, so in this first diagram up here to the left, you can see sensing done on a wind farm, then the diagnostics, prognostics, and finally the health management practices. And shown here to the right is how that all feeds into flow. So firstly, there's machine sensors. You take some data, you pre-process that data, classify faults, and extract features. And together, this is your CBM block. Whatever insights you get from this CBM block are further fed into the PHM block here, where there's prediction of how those faults are going to be evolving, and then actionable insights to schedule the required maintenance for those faults, rather than operators having to rely on time-based maintenance. Next, as organizations adopt PHM systems, they encounter several implementation challenges. These challenges can hinder the full potential of PHM systems, but there are proven solutions available to mitigate them. Let's explore the key challenges and how they can be effectively addressed. The first major challenge is legacy system integration. 47% of organizations report difficulties in connecting legacy systems to newer data-driven technologies. This oftentimes results from outdated infrastructure that lacks compatibility with current IoT platforms. Without IoT's Internet of Things, without integration, real-time data collection and analysis essential for PHM systems cannot be fully realized. The IEEE standards, such as the 1856-2017 PHM standard that we'll be talking about here shortly, and other standards, uh, play a crucial role in addressing this. By adhering to standardized protocols, companies can ensure compatibility across different systems and devices, facilitating seamless integration and data exchange. These standards offer clear frameworks for system design, reducing complexity and ensuring that legacy systems can work effectively with modern IoT platforms. So that's shown here in the diagram to the right, where there could be these older systems with intricacies and complexities uh, uh, that might hinder with their integration to newer stuff. PHM systems also generate vast amounts of sensor data, but 80% of this sensor data often goes unanalyzed, leading to inefficiencies. This is a significant problem as the raw data itself is of little value unless it's processed and turned into actionable insights. The challenge lies in really managing and analyzing these large data streams in real time. Edge analytics addresses this issue by processing data locally right at the source of the sensors. This approach reduces the need for sending all raw data to centralized cloud servers, cutting down on bandwidth and latency issues. With edge analytics, only the most relevant data is sent to the cloud for deeper analysis, optimizing both the data storage and the decision-making process. Next, implementing a PHM system can be expensive, with 60% of companies citing high costs as a major barrier. This includes the cost of installing sensors, acquiring necessary and analytic software, and setting up the infrastructure to handle data. For many organizations, the upfront costs can be a deterrent, even though the long-term savings from optimized maintenance and reduced downtime are substantial. To solve this issue, scalable cloud platforms provide a cost-effective alternative to traditional on-premise systems. With cloud solutions, organizations can pay for services as needed, reducing upfront investments and allowing for easier scalability. As the business grows, the cloud infrastructure can expand seamlessly without the need for major additional investments in hardware. As organizations adopt PHM systems, 70% encounter challenges with interoperability between IoT devices and systems. These challenges arise because various sensors and components often use proprietary communication protocols or formats, making it difficult for them to be integrated into a unified systems. Standardization initiatives like those promoted by the IEEE ensure that devices and systems adhere to common communication and data protocols. Lastly, with the increasing amount of sensitive operational data that is being collected, 50% of PHM systems are vulnerable to cyber threats. These threats can include data breaches, unauthorized access, and attacks on IoT devices. The risks of cyber attacks are particularly concerning when it comes to PHM, where system integrity and safety are paramount. Robust cybersecurity measures are therefore essential to protect PHM data. These include data encryption, multi-layer authentication, and the use of secure communication protocols. As PHM systems oftentimes involve cloud-based data storage and edge computing, ensuring that each layer of the system is secure is crucial for maintaining data privacy and integrity. Now we'll go ahead and take a look at the IEEE 1856 2017 PHM standard that defines the framework for PHM systems. It also provides guidelines for the design, implementation, and operation of PHM systems to ensure reliable monitoring, diagnosis, and prediction of the health of any given critical systems. This standard was released in 2017, and a couple people from Ridgetop have been on the standards committee. The standards now evolving into P1856.1 are recommended practices for PHM. And again, some of our Ridgetop folks are honored to be on that panel as well. So the standard comprises of 5 core PHM operational processes. The first one is sense, where data collection begins. Sensors and monitors capture critical data about the asset's physical or virtual conditions, such as temperature, pressure, vibration, and performance indicators, and this forms the a foundation for further analysis. The next one is acquire, where the collected raw data must be recorded, organized, and prepared for data analysis. This process includes data acquisition and data manipulation. Next is the analyze phase, where the PHM system applies advanced analytics to evaluate and predict system health. This includes 3 functional blocks: state detection, health assessment, and prognostic assessment. Next is the advice process. Based on the analysis, actionable insights and recommendations are generated. Operators and maintenance teams receive decision support information to plan maintenance activities. Um, and then lastly, we have the ACT process, where the system executes the recommendations through corrective or preventative actions. This ensures that the asset can return to a healthy operating state, reducing unplanned downtime and optimizing performance. To support these core operational processes, the PHM functional model includes 8 functional blocks that define the structure and workflow of the system. So for sense, we have the sensors that involves physical sensors and soft sensors to measure the asset's key performance and condition indicators. Sensors act as the data collection interface for the system. For acquire, we have data acquisition and data manipulation. Data acquisition acquires raw data from sensors, monitors, and system logs. It ensures that all necessary information is captured, recorded, and sent for further processing. Raw data is oftentimes noisy or incomplete, so the data manipulation block processes and transforms the data to make it clean and usable. Tasks include filtering, pre-processing, and quality control of the sensor data. Next, for analyze, we have state detection, health assessment, and prognostic assessment. For state detection, the system's current condition is evaluated by comparing sensor data with predefined baselines. Abnormal behaviors, flags, faults, and deviations from normal performance are identified. Health assessment provides insights into the asset's current health state by analyzing trends and faults. It also determines how severe the issues are and highlights and isolates areas that require immediate attention. Prognostic assessment forecasts the future state of health for the assets. It also predicts metrics such as the remaining useful life and identifies when critical failures might occur using predictive algorithms and machine learning techniques. For the advice process, we have advisory generation, which builds on the health and prognostic assessments to provide actionable insights and recommendations. These recommendations guide operators and maintenance teams on what actions to take. For example, what part should be replaced or when the repair should be scheduled. Lastly, for the ACT process, we have the health management block, which uses the insights and advice generated to take corrective or preventative actions. It ensures that the system returns to a healthy operational state, optimizing performance and reducing downtime. Together, these operational processes and functional blocks that we have talked about form an integrated system that supports real-time monitoring, predictive analytics, and proactive decision-making to ensure the overall reliability and performance of critical assets as mandated by IEEE. Next, I will turn the floor over to Gabby to talk about the importance of PHM for rotating components and the following.
Hi, everyone. Good morning. My name is Gabby. I am a software engineer here at Ridgetop. And for about the past year or so, I've been working on Sentinel Motion and kind of implementing everything that we've been talking about so far, and taking the process of PHM from the sensing to data acquisition to data manipulation, advisory, and health management forward. So as we talk about PHM, it's really important to focus on rotating components, which are the heart of many machines. So when we think about trains, aircraft, manufacturing equipment, wind turbines, and more, when those fail, like Arsh mentioned, it's not just a matter of downtime. These failures can lead to catastrophic consequences like derailments, equipment damage, costly repairs, and in critical applications like aerospace or power generation, the failure of these rotating components can pose serious safety risks. So as we look at some of these on screen, specifically when we talk about rail, right, we talk about detecting wheel and bearing defects to prevent those kinds of derailments. In aerospace, we can think about ensuring flight reliability, specifically in harsh environments, because those are harder to test for. Energy, when we look at wind turbines, we can definitely think about the proactive maintenance that can be done to avoid that costly maintenance. And also in industrial manufacturing, there's many components that have high vibration, dust-filled environments that are just a lot harder to maintain with those harsh environments. So yeah, these are some of the main reasons why looking at these rotating components in all of these different applications would highly benefit from PHM standards and implementations. Next slide. So as we look at some of these key technologies that are enabling these PHM systems, here at Ridgetop, over the last several years of development, we've developed many different systems and tools to complete the different blocks of the PHM requirements. Starting from the very beginning, sensors are the backbone of PHM. And we've developed a number of different sensors, vibrational sensors, temperature probes, gyroscope sensors to measure track geometry, and collect high frequency data from machines in real time. This data reveals patterns like unusual vibrations or temperature spikes, which can usually indicate early signs of failures. So as we look at RotoSense sensors, these are specifically for rotating equipment. So again, trains or turbines. And by extracting this high resolution vibrational signatures, we can start to analyze that data and pass it through onto the next blocks of the PHM processes. Some of the applications that we've used RotoSense sensors for are helicopters, CNC machines, wind turbines, gearboxes, and rail bearings. Another one of our sensors that we've developed is the smart probe, which measures voltage, phase, and frequency perturbations to identify early degradation in power systems. This early detection can also be applied to phase issues in power grids. And so not only are we taking that data that is being collected, but like Arsh mentioned earlier, that raw data on its own isn't really doesn't really tell us all that much until it's turned into actionable insights. So some of those techniques for analyzing the data is using the fast Fourier transform, also known as FFT. And so this converts time domain vibration data to frequency domain, and then that can be further manipulated to extract any information that would be relevant to the use case. We also use wavelet analysis, which detects transient faults and subtle anomalies. More specifically, in our Sentinel Motion application, we use the feature data extraction pipeline, which takes raw data and can be run through a number of different algorithms to then use those actionable insights in our AROL tool, which is the Adaptive Remaining Useful Life Estimator, which then will give us SOH and RUL predictions for any specified node. Yep, I think we can go to the next slide. Furthermore, after taking that sensor data, analyzing it, and then making that into real-time scalable data analysis, we use the Sentinel Gateway, which takes advantage of edge computing, which processes data on site for immediate analysis. Some cloud platforms allow for large-scale data storage and deep analytics. And together, these technologies really enable faster and smarter decision-making. And it also reduces latency and bandwidth needs, specifically for these mission-critical components, which oftentimes don't have the luxury of being able to send that data to a data center for further analysis, and having that data analyzed on-site in real time really helps capture any urgent needs that those components might have. Some other integrated features that we have in Sentinel Motion and across different Ridgetop products are dead reckoning GPS for location-specific correlations, and secure access points for log data to make sure that that data is always safe and it's not being exposed to any sort of cybersecurity threats or any of that. Yeah, we'll go ahead and go into the next slide. So looking into the future of PHM, as I mentioned, Ridgetop historically has kind of excelled in the first three blocks of the PHM functional model, which would be sensors, sensing, acquiring, and analyzing data. But as we move to the future and what the future trends look like, we really want to tackle those advising and acting processes. And some of the trends that are shaping the future of PHM right now are the use of digital twins. So digital twins, are basically a virtual replica of a physical asset, process, or system. They mirror the behavior, condition, and performance of its real-world counterpart by continuously receiving real-time data from sensors and other sources. So essentially, this is a live simulation of any component that you would have. So an example would be a wind turbine. If you have a digital twin of the turbine, it uses the sensor data to replicate its operations in real time. This enables you to monitor the health, predict faults, and test optimization strategies virtually without impacting the real machine. And this is a really good use of resources and helps reveal patterns like unusual vibrations or other things that can be signs of early failure. Another exciting trend in PHM is autonomous PHM systems, which is something that we've worked to implement a bit through Sentinel Motion. This goes beyond prediction and will automatically trigger different maintenance workflows based on predefined thresholds. So for example, in Sentinel Motion, you can monitor a node, set the definition for what a fault looks like, or what sort of warning signs you are looking for in that node, and then automatically trigger a set of data analytics and RUL or A-roll predictions. And based on that, you can trigger notifications to whoever is doing the maintenance, or in the future, hopefully, turn off a specific system if you see that the temperature is going too high or anything that's above a defined threshold that you've established. You can go ahead and automatically take care of that before a failure happens. Another trend that we're looking at is the use of edge AI for localized data processing. So we can have powerful AI models running on smaller devices directly on site. And this also enables real-time predictions even in remote areas with limited connectivity. So for example, some sensors on wind turbines can now process vibration data locally and identify faults within seconds. And I think there might be another slide. Yeah, all right. So yeah, just kind of to summarize the things that we've looked at today, PHM is a data-driven approach to predict and monitor the health of systems to prevent failures. We talked about kind of the evolution of maintenance practices, which is shifting from reactive maintenance to predictive and preventative models. We talked about the differences between CVM and PHM, where CVM focuses more on condition-based monitoring, while PHM really emphasizes forecasting failures and extending the life of an asset. We talked about the different challenges in PHM implementation, where some of those were data quality, system complexity, integration issues, and how the IEEE 1856 2017 standard provides guidelines for implementing those systems and also tackles some of those challenges that we talked about in PHM implementation. We talked about the importance of PHM for rotating components. So as we talked about, some of those rotating components are really critical for several different applications, and it's essential to be able to find those faults early and improve the system reliability. Some of the key technologies that are being used in PHM today and in the future. So machine learning, IoT, sensor technologies, and real-time data analytics, as well as some future trends. So increased automation, AI-driven insights, and integration with IoT systems. And that's kind of what we've got for you today. Arsh, I don't know if there was anything more you wanted to add. Okay, so it looks like we've got some questions in the chat. So the first question is, given the critical nature of data involved, what measures are taken to ensure data security and privacy in PHM systems, especially when used in aerospace and automotive industries? Yeah, so this is a really good question. So first and foremost, data and security, whoops, Data security and privacy are of the utmost importance when we're talking about PHM systems, particularly in crucial industries like aerospace and automotive, where sensitive and high-value data is continuously monitored and analyzed. So ensuring data integrity, confidentiality, and secure transmission is essential. Um, Specifically when we're looking at Sentinel Motion and edge computing, we use the gateway as a local asset to process the data locally. And by analyzing the data on site, the volume of information that's actually transmitted is really minimal. So that reduces the exposure to any external threats. So we're only sending essential insights such as fault detections or RUL predictions that minimizes any risk of data leakage. Um, Additionally, when we're thinking about data that's being transmitted from the sensors to the gateway, that's all protected via the firmware that we're using in the sensors. So it's all encrypted using protocols such as AES 256 encryption and also TLS and SSL protocols, which provide end-to-end encryption for any data communication. Um, so even if data is intercepted at any point during the transmission, it's remaining unreadable to any unauthorized parties. As far as when the data does go to a cloud or anything like that, we do use role-based access controls so that only authorized users can access or manipulate any data. And the gateway, the Sentinel gateway, acts as a secure access point, which ensures that log data is stored locally and securely. As far as compliance with industry standards, aerospace and automotive industries both adhere to pretty strict cybersecurity and data privacy standards. So Ridgetop and the Sentinel Suite all align with those standards and deliver safe, compliant PHM solutions. And then it looks like we have another question in the chat, which is regarding advancements in sensor technology, and which have been the most significant for enhancing accuracy of PHM systems, and how we select and position sensors for optimal data collection. So advancements in sensor technology have been instrumental in enhancing the accuracy and effectiveness of PHM systems. Sensors are essentially the first line of data acquisition, enabling precise monitoring of critical components like bearings and wheels. And some of the enhancements that have really made our tools work well are MEMS sensors, which are microelectromechanical systems, and they've revolutionized the PHM world by offering miniaturized, lightweight, and highly sensitive sensors that can monitor vibrations, accelerations, and temperature in real time. So sensors like RotoSense provide high-resolution vibrational signatures for detecting any misalignment, imbalance, or wear in rotating components. And not only are these sensors providing high resolution signatures, but they're also robust enough to operate in harsh environments. So anything like aerospace, rail, and industrial applications, they'll really do well in. Another thing that's really revolutionized sensing in this space is the fusion of multi-sensor technologies. So when we think of different types of streams of data that are coming in, the sensors that we use can have all of those data streams, so vibrational, temperature, pressure, gyroscope, and that really provides a holistic view of the component's health. So individual sensors, when they're only doing one stream of data, might have they might miss any faults when operating in isolation, but multi-sensor fusion integrates different various data streams to improve accuracy. So, for example, rising temperatures alongside with unusual vibrational frequencies is usually a pretty strong indicator of a bearing failure. And to answer the second part of the question, um, about positioning for optimal data collection. Um, oh, So positioning for optimal data collection. The first step here really is to identify the different fault modes. So sensors are selected based on the different types of failures that we're looking to detect. So vibrational sensors detect mechanical faults like imbalances, misalignment, and wear. Temperature sensors monitor for any thermal anomalies that might signal overheating. Gyroscope sensors might be looking for any track geometry to identify any areas of the track that might be misaligned that could cause derailment or anything like that. Um, for example, in wind turbines, vibration sensors monitor the gearbox while temperature sensors track any heat buildup. And then positioning those sensors near the critical stress points is also of huge importance. So anything like sensors, yeah, sorry. Sensors could be placed where stresses, vibrations, or failures are most likely to occur. So placing the sensors near a bearing or a shaft are close to the components that capture rotational imbalances and wears. If we're looking at gearboxes, placing the sensors at any input or output shafts might help identify misalignment and gear tooth damage. And when we're looking at rail, placing the sensors on axles might detect any early signs of bearing failure or flat spots. And then another question in the chat are how are PHM systems integrated with existing infrastructure in harsh environments? And what are the primary technical challenges faced during this integration? So this is another really good question. So integrating PHM systems into existing infrastructure, especially in harsh environments like rail, requires careful consideration for both hardware and data flow. So a couple things that we need to look at there are the adaptability of the sensors. So sensors like RotoSense are designed to withstand extreme conditions, anything like vibration, dust, temperature, and humidity, without compromising any of the accuracy. And wireless and compact designs make them ideal for hard to access locations like rotating shafts or helicopter gearboxes. And then another thing that we need to look at is edge computing for real-time processing. Things like the Sentinel Gateway process sensor data locally, which reduces any reliance on internet connectivity for remote environments, and that minimizes latency. And then the last thing that we need to look at is any technical challenges. So any environmental stress that the sensors might be going to, power supply challenges, and then data transmission to make sure that the data communication is secure and reliable. And by leveraging like rugged hardware, edge computing, and robust sensor technologies, PHM systems like the Sentinel Suite and Sentinel Motion are successfully integrated to monitor critical assets in the most demanding conditions. So yeah, those are a couple of the challenges, but all right, well, I guess if there's not any more questions, we'll go ahead and wrap it up here. Thank you so much, everyone, for joining and for your insightful questions. And yeah, we'll go ahead and wrap it up and share the link and the slide deck, everyone.